Nice. Okay. Today we start our second uh, module. Uh, Name of its model is dynamic programming. And today we will start with the several tasks of dynamic programming. Unfortunately, I have no presentation today, but I think that we can save this board after the lecture and send it to the students. Yeah, do we have this? Yeah, nice. So about dynamic programming and common theory about it. Yeah, today we talk about dynamic programming part 1. And so this lecture and next lecture uh, consist of many different tasks in which we find in the solution of which we find methods equal to names as dynamic programming. So I think there is no it's one way to understand dynamic programming as the set of methods that can you use when you solve some problems. So, firstly, about common theory um, under this topic. About some reasons why you can use dynamic programming and don't use any other algorithms. Firstly, you can find different tasks. Yeah. Uh, you have tasks. In which you find two main parts that show you that you need to use these these methods. Firstly, you can split your tasks for some subtasks. And it's the first step. It's the first main part of the dynamic programming. And the second important step that you can solve these subtasks independently. And we find these two steps in next examples. that we talk about today. But you can see that it's very common language that we can talk about the problem. And of course, dynamic programming is equal to different recursive algorithms. But as we see, in different tasks, we find ways that we can use dynamic programming is more comfortable than the recursive analogous. So it's about steps or main part that we need to find in the tasks to use dynamic programming. And then, for example, how we use what is the difference between dynamic programming and recursive algorithms? For example, you know what is Fibonacci numbers? Yeah. You know that f0 equal to 0, f with the index 1 equal to 1. And we have recurrence formula for them. Yep. So, for example, we need to find, for example, f with the index 5. Yeah. How we can find it? Recursive, for example, yeah, we can use this formula and say that to find f5, we can find f3, and we find f4. Yeah. Then we can say that we don't know f with the index 3, and we can repeat these recursive algorithms. Yeah, we say that it equal to f1 plus f2. Yeah, f1 we know, f2 we don't know, and we repeat it. And we repeat this algorithm for this part of this tree. Yeah, and we see that, for example, for f with index 5, what is the number of subtasks that we need to solve? Yeah. For example, you can say that node is equal to one subtask. Yeah. For example, we need to find f with index 3, and then number of the nodes has exponential or asymptotic. Yeah, you see. So, yeah, native recursive algorithms has asymptotic time equal to 2 power n. You know it from the other courses, yeah? you know this asymptotics from the other courses. Yeah. So how we can solve this task to find Fibonacci numbers in the way to spend less than exponential time for it? You don't? Or do you know? What is the time? Or guys in the Zoom can say? Yeah, to avoid exponential growth of the subtasks, number of subtasks. We can find, yeah, of course. Interesting, yeah. Ways to prevent large spans, time spans. Also, we can use analytic formula for Fibonacci numbers. Have you ever seen the analytic formula for Fibonacci numbers? Yes? It's equal that Fn equal to C1, 1 in, yeah. Yeah, you see it, yeah. With some coefficients and lambdas. Okay, but for example, if we change this recurrent formula, we need to get paper, find analytic formula, and of course to find these two number, lambda 1 and lambda 2, we need to solve some polynomial equation. And of course, in the general way, we need to use some approximation algorithms to it, and this way has its own reasons to not use it. Because of analytic formula, we have no analytic formula for difference recurrence if it isn't a linear recurrence. So, for example, if I add this power 2, you cannot use common way to solve the linear recurrence equations. So, of course, this way we can use to solve this task for Fibonacci numbers, but in the common way, this way will be too complicated as the native way. So, second way that we can use to solve this task, we can say that we have very similar subtasks. We can say, for example, yeah, that here we have two subtasks to find F2, F3, and it's... I think we can complete F3 one time. Yeah, and then we can use it. Yeah, of course. So, of course, we can say that we can find in this tree similar subtasks, yeah, to find for example, Fibonacci number with index 3. And then if we one time find the solve this task, we can store this information and use when we find it in the tree again. So second way to we can use dynamic programming in this task is that we can say that we can store the results of subtasks. And then if we find a similar subtask, we we won't spend time for complete it. We see in the memory, yeah, and find the result of this task, of this subtask. And this way to store the results of subtasks names as memorization. Because we can use memory to spend to decrease number of subtasks that we need to solve in the solution of our common task. Okay.
Memorization. Where should we stop memorizing?
When we start our algorithm, we get, for example, this number. It's equal to. We said that it is equal to n, and then we finish when we find this result of this task. And of course, in the different tasks, I write now here. In the different tasks, we can use different structures. For memorization. And our dynamic algorithm ends when we find the results of our task. It's understandable. Yeah. When we find the results of initial task. So in this example, yeah, why it's so annoying?
You wrote erase it 2 times.
Oh, think. Yeah. No. Okay. In this task, task of Fibonacci numbers, we can say that if we need to find Fn, we can find F0, F1, F2, F3, etc. and store these numbers. So when we need to find Fn, f with index n, we can pop number f with index n minus 1, repeat it for f with index n minus 2, and find the sum of these two numbers. So if we see this algorithm, when we find initial number of Fibonacci numbers, then we repeat to find f with index n, we repeat our algorithm, we repeat this formula and find the new number by it. So, as we see that time complexity of the solution is equal to, what is the time complexity? Linear, yeah. It is equal to O from number of Fibonacci number, index of Fibonacci number that we need to find.
In the negative equation, it will be log n,
right? No. Here we have exponential time space complexity. So, yeah, 2 power n. It is time complexity. And due to this time, we want to find other way to solve this task, because exponential time is very big in a lot of cases. So, but what is we can say that native algorithm is worse than this dynamic algorithm due to time complexity. But in which way native algorithm will be better than the dynamic algorithm? Do you know?
Memory?
Memory. Yeah, because of memory. And of course, we say that to solve this task with dynamic algorithm, we need to use memorization. We need to store previous Fibonacci numbers. And of course, if we use, for example, array, for Fibonacci numbers. We say that space complexity O from n, because we need to store previous numbers. And of course, we can say that due to this formula, we can store only previous two numbers and change it in each step. And then we change this asymptotic complexity to O from 1. And of course, it will be better, but it works only due to this very simple task. And in the other task, we cannot upgrade it with decreased number of storing numbers. So when we use dynamic algorithm, if we use dynamic algorithm to solve some tasks, we need to understand that we change the increase the lower time complexity to bigger space complexity. Yeah, we change. So we need to understand, is it better to store bigger data and get the speed up in the time complexity, or use other algorithm and have no problems with the memorization? Because, for example, in this task, we need to store only integer number, and memory that we use for it very small, and a lot of language properties or properties of hard memory become more quicker solution of this storing, because of a lot of using of integer numbers. But for example, if one result of the subtask is equal to, for example, a big text, for example, or some structure. So if we store linear, for example, if we store n such structures, we can spend a lot of time to make it, to connect it between each other. So you can understand when we use such algorithm, we need to understand how much we spend to memorization, of course. How much we spend to memorization. And it is common theory, and then we need to spend our time to different tasks to understand why dynamic programming is better than other algorithms, and we see it with the other tasks. I see now first I want to talk about longest increasing subsequence.
Sorry,
Yeah.
but I didn't understand why we need big O of n for memorization in Fibonacci example.
Can you repeat what we?
I didn't understand why we needed space complexity of big O of n to in the dynamic way.
Why we spend O of n space complexity for
Yes,
this realization? Because if we store Fibonacci numbers from 0 to fn, we spend we need to store n numbers, and we get O at n, O from n space
But-
complexity. Yeah.
but we don't need the n Fibonacci numbers.
Yes, that's why you can be.
Yeah, so I write that in this task we can
Okay.
improve it to O from 1, of course. But in some tasks we need to store O from n, not in this task, but in the most tasks that we use dynamic algorithm, we cannot improve this space complexity. And we see in the next task that we can store a lot of data to get less number of subtasks that we need to solve. So I write here that we change time complexity, yeah, to space complexity. And of course here we can improve this algorithm such that we cannot spend anything, and we cannot spend a lot of space and get the speed up in time from exponential to linear. But in the next task we see that we can improve the time complexity and get the speed up. But in this way we spend bigger space to store some data. So in this task you're right that we can not to store all of these Fibonacci numbers and store only pair of these two Fibonacci numbers. Yeah, we firstly store these two Fibonacci numbers, then we change it with this pair. Let's try, and finally we get pair of these two Fibonacci numbers. And you're right that if we change array to this pair of integers, we spend only O from one space to it. But it's due to this simple task, because of Fibonacci numbers, it's I think training tasks for this topic. But now we face with other tasks and see that of course we cannot increase we cannot decrease space complexity. Yeah. Do you understand?
Yes, thank you.
So, about the second task, about longest increasing subsequence, it's interesting that in the there are two tasks that I want to talk about. Firstly, imagine that we have sequence of integers. Here we have a with index 1, a with index 2, etc., a with index n. And input data, it's n and this sequence. And we need to find subsequence a with index n1, a with index n2, etc., a with index nk, such that, of course, it is the subsequence of the of this sequence, and it is equal that n1 minus n2, etc. Here is due to definition of subsequence.
N1 or N1?
Hmm?
N1 or
N1,
N2?
N2, and we say that the indices of this A will be increasing sequence, and of course it is first. And the second that A n1 yeah, due to increasing sequence. So now we can find this. What is the native algorithm for it? For there are different ways to improve the algorithm. Firstly, I can say that it is two exponential algorithm that we can check all the subsequences of this sequence. Yeah. You can check all subsequences is it increasing or not? So, what is the time complexity of this solution? How many subsequences in this sequence?
N to the power n?
2 power n, yeah.
To the power n.
2 power n. Because any this number can be in subsequence or not in this subsequence. And then we find production of this variance. So, and space complexity? is equal to O from 1. Because, for example, we can set iterator from 0 to 2 power n minus 1. And then we find this sequence by this number, and don't spend any other space. Or we can store, yeah, we need to store this sequence, so we need to use, yeah. So we need, yeah, it's equal to n because of storing this sequence. Yeah, of course.
I didn't understand why we need 2 to the power n. The time complexity. Can you please explain me?
Time complexity, why it is equal to, okay. Can you ask yourself how many subsequences or subsets, yeah, in the set 1 to n? Are. How many subsets are in this set from 1 to n? 2 power n. And for each subsequence, we can say that this subsequence we can code with this sequence of integers n1, n2, and k, and it is the subset of set of from 1 to n. So time complexity is equal to 2 in power n due to a number of subsequences of this sequence. For example, yeah. Oh. If n equal 2, and we have sequence A1 and 2, we need to check sequences A1, A2, A1, A2, and empty sequence. So number of these subsequences is equal to 2 power n 4. Do you understand? Yeah?
Yes, thank you so much.
Okay. So, of course, it is native algorithm, yeah, and of course we can improve it because we understand that, for example, if subsequence is increasing, so any subsequences is too increasing, and we need to find, for example, subsequences that ends in place that we choose, for example. So the second way that we can improve first algorithm, we can say that for each a with index k, we can find the longest increasing subsequence that ends with AK. So, how we can find this subsequence? Interesting that if we use different structures to store previous longest increasing subsequences, we get different time complexities in the algorithm. Firstly, we can say that we can store the length of the longest increasing subsequences for all numbers from A1 to A with index k minus 1. We can store it for the previous numbers. So if we know that what is the length of the longest increasing subsequence that ends in a k minus 1, a k minus 2, a k minus 3, etc. a1. We say that we can check if am minor than ak. We think that the numbers are different. So if there can be equal, I say that it can be less or equal to right part of this inequality. And if now I write some pseudocode of it, yeah. If you find am less than ak, for these numbers, we can compare their lengths
K and M. Which one is bigger?
m minor than k. Of course. And if we find am such that it is less or equal than ak, we can say we know for this number that the biggest subsequence that ends in am has length Lm, for example. So we can add to this subsequence ak because of this inequality and increase this subsequence. Yeah, so I can erase this if.
So here, k is equal to m plus 1.
Hmm?
K is equal to m plus
No, it can be bigger than m, but not equal to m minus plus 1. And so for such am that am less than ak, we find the biggest number Lm. And for example, the biggest number Lm is equal to alpha, and we said that Lk is equal to alpha plus 1, because we find the longest subsequence that end in am, and length of this subsequence equal to Lm, and we add ak to it. So the length of this subsequence equal to L with index m plus 1. I can write this algorithm steps by step. Yeah. So algorithm. Firstly, make empty array L n and set each Ln equal to 1. Because of course we know that the subsequence can be can consist only from one number, and it can be equal to and then this subsequence has length equal to 1. Then we set, for example, we set iterator to for each we go from 1 to it minus 1 and compare am and ak, yeah? We change m from 1 to it minus 1. And if am less than ak, we say, okay, then we can find the longer subsequence. And how we can find? We say that L from iterator will be maximum of the length that we have already found and the length of this subsequence, this subsequence that we now find in this step. So what is the length of this subsequence? It's equal to L from M plus 1. And we increase it and repeat second step while it's less than n. So when we get this array and we find all increasing subsequences that we find the longest subsequences, increasing subsequences that end in with the number a n. Then we say that the longest increasing subsequences in all sequence will be the maximum of this array. So the answer is maximum of this array. Do you need to make example of working of this algorithm? Guys in the
I think yes.
Yes, okay. So example, if n equal to 8 and we have, for example, this, for example, it's equal to a1, a2, a3, etc. And then it says that L initially is equal to L equal to 1, 1, 1, It's the first step. And it's equal to then we repeat second step. We say for A2 we find A1 minor than A2. Yeah. So L of 2 is equal to maximum of L1 L2 L1 plus 1. Yeah. So it's equal to 1, it's equal to 2, and so it's equal to 2. Yeah. And then we end of this step because we got this number. And then we set iterate equal to 3 and go to step 2. Yeah, I write these numbers over the numbers in this sequence. Yeah, the longest increasing subsequence that ends with the first number equal to 1. Here 2. Here we compare A3 and previous A and say that there are no numbers such that they are less than A3. So it's equal to 1. Yeah. So no AM such that M higher than A3. So we repeat. Yeah, we set iterator equal to 4. Go to second step. And then
I think it's understandable now.
Oh, it's
I don't
understandable.
have, yeah,
Nice.
yes.
Yeah. So what is the L from 4? 4. Yeah. It's equal to 3. Because we can find this subsequence. We find that A with index 4 bigger than the previous numbers, and then we find the maximum of these 3 numbers and get plus 1 for it, and get the length of the longest increasing subsequence that end with the 4th number. For this number, 4. For this number? No. 21 is less
It's
than...
smaller.
Yeah, it's 4 too. For this number?
Also 4?
No. Because 4 is less than 8. No, not 2. It's equal to 3. Because 4 is bigger than this number, and this number. And we compare these 3 numbers and find the maximum, it's 2. And the length of the increasing subsequence that end with this number will be 2 plus 1. Why? For this number, it's equal to 1. Yeah.
Yes.
So after that, yeah, we say that the maximum of this number is equal to 4. So 4 answer. And of course, we can find, if, for example, we store the link for the previous number, not only the number, we find that this number can connect with 8, it connect with 3, we connect with 2, and then we find this subsequence. So, of course, if we need to find not only the number of the numbers in the longest increasing subsequence, we can store links and then find such subsequence with these lengths. So, okay. Of course, we need to understand what is the space complexity. And time complexity of this algorithm. Linear, yeah. How many times? Oh, yeah, n square. Yeah, because for the second number, we repeat comparison 1 time, for the third 2 times, etc., and we get the sum of 1, 2, 3, etc., n minus 1. So it's equal asymptotically to n square. So, of course, it's better than 2 power n. But we can solve this task with time O n log n. So, do we need now break time, or we talk about the third algorithm for solve this task, and then we get break time?
Do the dynamic way and then go to break.
Okay. So about the yeah, about this increasing. Now, what do we store now in the third algorithm, or in the second algorithm? We thought the length of the increasing of the longest increasing subsequence such that the end number is equal to a with index k. But we can use in this way different array that we store and upgrade each step. We can change n to, for example, yes, or fix array. And when iterator will be equal to key, fix from E. I think, yeah, when it will be equal to key, fix from E will be equal to number am such that there are there exists the increasing subsequence with the length E. And such that there exists the increasing subsequence with the length E, and ends is am. And it is the minimum of such numbers. So you can try to understand how we will use this array to get this time complexity. And now we get break time. So if you want to talk about your theoretical test, we can talk now about it. And do you set the recording to the pause?
Yeah.
No.